Welcome to the Sleepless Universe. In this video, we will explore the strangest stars ever discovered, from the super-dense neutron stars to the mysterious and hypothetical quark stars, and many more cosmic wonders in between. If you enjoy this kind of content, I'd be happy if you left a like and subscribed, and write in the comments where you're watching from and what time it is for you. Now, I wish you a relaxing journey and lots of enjoyment while listening. Neutron stars. In the vast cosmic theater, few objects are as extreme, mysterious, and awe-inspiring as neutron stars. These stellar remnants are born from the catastrophic deaths of massive stars, and in their small, city-sized spheres lies a universe of unimaginable density, gravity, and exotic physics. To understand neutron stars is to stand at the frontier of astrophysics, where matter itself is pushed to its ultimate limits, and the familiar rules of nature twist into strange new shapes. Neutron stars begin their existence in the fiery heart of a massive star that has burned through its nuclear fuel. For millions of years, a massive star maintains a delicate balance between the outward pressure from nuclear fusion and the inward pull of gravity. In its core, hydrogen fuses into helium, helium into carbon, and heavier elements until iron is formed. But iron is a dead end for nuclear fusion. Fusing it does not release energy. When the core becomes iron-rich and massive enough, gravity takes over. In a fraction of a second, the core collapses under its own weight, crushing atoms so tightly that protons and electrons merge to form neutrons. This is the moment when a neutron star is born. The outer layers of the star are blown away in a titanic supernova explosion, releasing more energy in seconds than our sun will emit over its entire lifetime. What remains at the center is a sphere of pure neutrons, typically just 20 kilometers across, yet containing more mass than our sun. To grasp this density, imagine compressing Mount Everest into the size of a sugar cube, and then realizing that you are still underestimating the weight. A single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The physics inside a neutron star is unlike anything we can replicate on Earth. The outermost layer, called the crust, is made of a rigid lattice of nuclei, immersed in a sea of degenerate electrons. Beneath this crust lies the neutron superfluid, a bizarre state of matter where neutrons flow without friction, swirling in quantum vortices. This superfluid is thought to play a role in the sudden changes in rotation at speed observed in some neutron stars, events known as glitches. At the core, the pressures and densities may be so high that even neutrons break down into their constituent quarks, possibly creating a quark matter core. If this is true, neutron stars might be natural laboratories for studying matter, at densities far beyond those achievable in particle accelerators. One of the most striking features of neutron stars is their gravity. Because they pack so much mass into such a small volume, their surface gravity is about 200 billion times stronger than Earth's. If you were somehow able to stand on the surface, ignoring the fact that you would be instantly crushed, lifting your foot would be impossible. Light itself struggles to escape, bending noticeably under the star's immense gravitational field. This effect is so strong that if you could see a neutron star up close, you might be able to view parts of its surface that would normally be hidden behind its curvature, as the light curves around the star before reaching your eyes. Another fascinating aspect is their rapid rotation. When the core of a massive star collapses, it spins up much like an ice skater pulling in their arms. Some newborn neutron stars rotate hundreds of times per second, their incredible speeds maintained by the conservation of angular momentum. Over time, they slow down, but many remain fast enough to generate powerful magnetic fields. These magnetic fields can be trillions of times stronger than Earth's, making neutron stars some of the most magnetic objects in the universe, a property that links them to another strange category we will meet later: Magnetars. Neutron stars are not just silent cosmic relics. They are dynamic and sometimes violent. They can produce bursts of X-rays or gamma rays when they accrete matter from a companion star, heating the infalling gas to extreme temperatures. Some are found in binary systems, locked in tight gravitational dances that can lead to spectacular events. In rare cases, two neutron stars may spiral into each other, emitting gravitational waves, ripples in the fabric of space-time. and producing kilonova explosions that forge heavy elements like gold and platinum. The detection of gravitational waves from such a merger in 2017, known as GW170817, was a milestone in modern astrophysics. It confirmed not only that neutron stars merge, but also that these mergers are a primary source of heavy elements in the universe. This event was observed across the electromagnetic spectrum, from gamma rays to radio waves, marking the birth of multi-messenger astronomy, the practice of studying cosmic phenomena through both light and gravitational waves. Neutron stars also challenge our understanding of the equation of state, the relationship between pressure, density, and temperature, for ultra-dense matter. By measuring their masses and radii, astronomers hope to uncover whether exotic states of matter, like hyperons or quark matter, exist in their cores. Observations from NASA's Neutron Star Interior Compositions Explorer, NICER, mounted on the International Space Station, have already provided unprecedented insights into their structure. For all we know about them, neutron stars remain deeply mysterious. Their extreme conditions make them natural testbeds for the laws of physics, allowing scientists to explore regimes far beyond our earthly laboratories. Each observation is a clue, a step toward understanding not only these strange stars, but also the fundamental forces that govern the universe. Neutron stars stand as monuments to the violent deaths of massive stars. Yet they are also gateways to knowledge, holding in their dense hearts the answers to questions about matter, energy, and the very nature of reality. And as we will see in the coming chapters, they are just the beginning of the cosmic menagerie of strange stars that populate our galaxy. Their study is not without challenges. Neutron stars are small and incredibly distant, which makes them difficult to observe directly. Most of what we know comes from their effects on their surroundings and from the signals they emit across the electromagnetic spectrum. In some cases, we detect them as radio pulsars, emitting beams of radio waves that sweep past Earth with clock-like precision. In others, we observe X-ray emissions from hotspots on their surfaces or from accretion disks formed when they draw in matter from a companion star. The more wavelengths we observe, the richer the picture we can form of their behavior. Astronomers also make use of timing measurements to probe the internal structure of neutron stars. Because many pulsars rotate so consistently, even tiny deviations from their expected timing can reveal seismic shifts within their crusts or subtle interactions in their magnetic fields. These measurements require patience and precision, sometimes spanning decades of observations. The reward is a deeper understanding of how matter behaves at densities that defy conventional physics. One particularly intriguing line of research focuses on neutron star cooling. After their formation, neutron stars begin incredibly hot, with surface temperatures reaching millions of degrees. Over time, they cool as they radiate energy into space, but the rate of this cooling depends heavily on the physics of their interiors. Some observations suggest that superfluidity in the core accelerates cooling, while other data points to more complex processes involving neutrino emissions. These faint, ghostly particles escape from the star's interior, almost unimpeded, carrying away enormous amounts of energy and offering clues about the star's inner composition. Then there are the spectacular outbursts and flares. While most neutron stars are relatively stable, some can unleash sudden bursts of high-energy radiation. These can be triggered by starquakes, when the crust cracks under the strain of the star's magnetic field or rotation. The resulting release of energy can briefly outshine entire galaxies in X-ray or gamma-ray light. These events remind us that, despite their stability over millions of years, neutron stars are anything but static. Our understanding of neutron stars has also been enriched by simulations and theoretical modeling. Supercomputers are used to model their formation, structure, and interactions, taking into account the complex interplay of gravity, quantum mechanics, and nuclear physics. These models can be tested against observations, refining our theories and sometimes overturning long-held assumptions. For instance, recent models suggest that neutron stars might have layered structures with exotic forms of matter, sandwiched between the crust and the core, a possibility that could be confirmed with future gravitational wave detections. Culturally and philosophically, neutron stars occupy a fascinating place. They are symbols of extremes, the densest stable objects in the universe outside black holes, born from cataclysmic destruction, yet persisting for billions of years. They remind us that even in cosmic death, there can be enduring beauty and complexity. Their very existence challenges human intuition, forcing us to grapple with concepts like space-time curvature, quantum states of matter, and the sheer power of gravity. Looking ahead, the next decades promise even greater discoveries. New radio telescopes like the Square Kilometer Array will detect thousands of new pulsars, while space observatories will map their X-ray emissions in unprecedented detail. Future gravitational wave detectors will pick up fainter and more distant neutron star mergers, allowing us to peer deeper into cosmic history. As our tools improve, so will our ability to answer the lingering questions. How massive can a neutron star become before collapsing into a black hole? Do they all share the same internal structure, or are there hidden variations? And could the cores of some harbor exotic matter never before seen in the universe? Neutron stars are the perfect introduction to the world of strange stars, not because they are the rarest, but because they represent the first step into the truly bizarre. They are our gateway into a realm where the familiar rules of matter give way to something alien, yet still governed by the same fundamental forces. From here, the journey will only grow stranger as we move on to stars that flash like cosmic lighthouses, generate the most intense magnetic fields known, or perhaps exist only in the realm of theory. Pulsars. If neutron stars are already among the strangest objects in the universe, pulsars are perhaps the most mesmerizing and precise of them all. They are neutron stars that announce their presence to the cosmos with rhythmic bursts of energy, spinning with an accuracy that rivals the finest atomic clocks on Earth. Imagine a cosmic lighthouse, its beams sweeping across the universe at intervals so regular that astronomers can predict its flashes years in advance. This is a pulsar, a rotating neutron star whose magnetic axis is misaligned with its rotational axis, causing its powerful magnetic fields to sweep beams of radiation through space. The story of pulsars begins in 1967, when a graduate student named Jocelyn Bell Burnell noticed an unusual signal while analyzing data from a radio telescope at the University of Cambridge. The pulses were so regular, about once every 1.3 seconds, that at first they were jokingly labeled LGM for Little Green Men, as if they might be signals from extraterrestrial civilizations. But soon it became clear that these were not messages from aliens, but the fingerprints of an entirely new class of astronomical objects. This discovery earned the 1974 Nobel Prize in Physics for her supervisor, Anthony Hewish, though Bell Burnell herself was famously overlooked, a decision still debated in the scientific community. Pulsars rotate at astonishing speeds. Some, known as millisecond pulsars, spin hundreds of times per second, completing a full rotation in less than the blink of an eye. This rapid rotation is a result of the conservation of angular momentum from their progenitor stars, often sped up further when they siphon matter from a binary companion. As material falls onto the pulsar, it transfers angular momentum, spinning the star up to incredible speeds. These systems are often referred to as recycled pulsars because the older neutron star gains new life as a rapidly spinning, highly stable beacon. The beams emitted by pulsars are the result of intense magnetic fields, trillions of times stronger than Earth's, accelerating charged particles to near-light speeds along their magnetic poles. As these particles move, they emit radiation in a tightly focused beam, usually in the radio spectrum, but sometimes in visible light, X-rays or gamma rays. If Earth happens to lie in the path of one of these beams, we detect a pulse each time the beam sweeps past us, much like watching the beam of a lighthouse as it turns. What makes pulsars truly remarkable is their timing stability. Some pulsars keep time so precisely that their signals can be used as cosmic clocks, accurate to within a few billionths of a second. This stability has allowed astronomers to use pulsar timing arrays to search for gravitational waves from supermassive black hole binaries. By carefully measuring tiny variations in the arrival times of pulsar signals across the sky, researchers can detect the subtle stretching and squeezing of space-time caused by passing gravitational waves. Beyond their utility as timing instruments, pulsars are also astrophysical laboratories. Their extreme densities and magnetic fields provide natural conditions that cannot be replicated on Earth. Observing how their pulses change over time can reveal information about the star's internal structure, magnetic field evolution, and even the interstellar medium between us and the pulsar. Variations in pulse arrival times can also indicate the presence of planets orbiting pulsars, a discovery first made in 1992 when astronomers found the first known exoplanets around the pulsar PSRB 1257+12. These planets, likely formed from the debris of the supernova that created the pulsar, are bathed in lethal radiation, but serve as proof that planetary systems can arise in even the harshest environments. Pulsars also display some of the most exotic phenomena in astrophysics. One such effect is pulse nulling, where the pulsar's beam seems to switch off for seconds, minutes, or even hours before resuming its regular pulses. The cause of nulling is still uncertain, though it may be related to changes in the pulsar's magnetosphere. Another is mode changing, in which the pulse shape or intensity changes abruptly, suggesting a reconfiguration of the star's magnetic field structure. Then there are glitches, sudden increases in rotational speed, likely caused by the shifting of superfluid components in the star's interior, briefly transferring angular momentum to the crust. Millisecond pulsars hold a special place in pulsar research. They are the fastest rotating neutron stars known, with the record holder PSRJ 1748-2446 AD, spinning an astonishing 716 times per second. To put this into perspective, the surface of this pulsar is moving at about a quarter of the speed of light. Despite such extreme conditions, millisecond pulsars are extraordinarily stable, making them ideal for high-precision timing experiments. Some pulsars are also incredibly bright, not just in radio, but across the electromagnetic spectrum. The Crab pulsar, for example, is the remnant of a supernova observed by Chinese astronomers in 1054 AD. It emits pulses in radio, optical, X-ray, and gamma-ray wavelengths, making it a cornerstone of multi-wavelength astronomy. Each pulse from the Crab pulsar is a reminder of a star's violent death nearly 1,000 years ago, and its study continues to yield insights into neutron star physics and the behavior of relativistic particles in strong magnetic fields. The environments around pulsars can be equally fascinating. Pulsar wind nebulae, like the Crab Nebula, are created by the outflow of relativistic particles from the pulsar's magnetosphere. These winds interact with the surrounding supernova remnant, producing glowing clouds of gas and dust that can span light years. The intricate filaments and structures in these nebulae are shaped by both the pulsar's wind and its rotation, creating some of the most visually stunning objects in astronomy. Some pulsars are part of exotic binary systems, where their extreme gravity and radiation interact dramatically with a companion star. In Black Widow systems, the pulsar's intense wind of high-energy particles strips material from its companion, sometimes eroding it down to planetary mass. Even more extreme are redback systems, where the companion star is more massive but still subject to the pulsar's destructive influence. These binary interactions can lead to changes in the pulsar's rotation and emission properties, adding further layers of complexity to their study. Perhaps the most dramatic role pulsars play in the cosmos is as cosmic probes, helping us measure and map the universe in ways that no other objects can. Their extraordinary timing precision allows astronomers to detect the tiniest gravitational effects, such as the Shapiro delay, where pulses take slightly longer to reach us when passing through the gravitational field of another massive body. This effect has been used to test general relativity with exquisite accuracy, confirming Einstein's predictions under some of the most extreme conditions known. Pulsars have also proven to be essential tools for navigation. In theory, spacecraft could use pulsar signals as a kind of cosmic GPS. By measuring the arrival times of pulses from multiple known pulsars, a probe could triangulate its position anywhere in the galaxy, independent of Earth-based tracking systems. NASA has already tested this concept with the Sextant experiment aboard the NICER telescope on the International Space Station, successfully determining its position using X-ray pulsar signals. One of the most enigmatic subcategories is the magnetar-like pulsar, a hybrid that exhibits properties of both pulsars and magnetars. These rare stars blur the line between the two classifications, sometimes switching from regular pulsar activity to intense X-ray flares. Studying them may help astronomers understand the evolution of neutron stars and the ways in which their magnetic fields decay or transform over millions of years. The life cycle of a pulsar can be surprisingly long. Newly formed pulsars, spinning rapidly and emitting powerful beams, gradually lose energy and slow down. Over tens of millions of years, many fall below the pulsar death line, a point at which their beams are no longer detectable. Yet, under the right circumstances, a dead pulsar can be recycled if it begins accreting matter from a companion star, spinning up to millisecond periods and re-emerging as an active beacon. This process shows just how dynamic neutron star evolution can be, with a single object transitioning through multiple states over its lifetime. There is also a tantalizing connection between pulsars and some of the most energetic explosions in the universe. Certain gamma-ray bursts, brief, intense flashes of high-energy radiation, may be powered by newborn magnetars or rapidly spinning pulsars left behind after a supernova. In these scenarios, the rotational energy of the pulsar is converted into powerful outflows that can be detected billions of light-years away. If confirmed, this would link pulsars to events visible across most of the observable universe. While pulsars are primarily detected through radio astronomy, they are far from limited to that wavelength. The Fermi Gamma Ray Space Telescope has identified hundreds of gamma-ray pulsars, many of which are invisible in radio. Some pulsars also produce pulses in visible light, a rarity that offers unique opportunities for ground-based observation. Each new detection adds to the diversity of pulsar behaviors, challenging existing models and hinting at the possibility that we have yet to see the full range of what these stars can do. The significance of pulsars extends beyond astrophysics into the realm of human imagination. They have appeared in science fiction as navigational aids, communication devices, and even as beacons left by ancient civilizations. While these fictional interpretations often exaggerate their properties, they reflect a truth about pulsars. They are among the most precise and enduring signals in the universe, capable of outlasting human civilizations by millions of years. As our technology advances, so too will our understanding of these cosmic lighthouses. The Square Kilometer Array, once operational, will discover thousands of new pulsars, including many in distant parts of the galaxy. This expanded pulsar catalog will improve our gravitational wave detection capabilities, map the interstellar medium with greater detail, and potentially uncover entirely new types of pulsars. With each new discovery, the story of these remarkable stars becomes richer and more complex. Pulsars are the rhythm section of the cosmos, their steady beats echoing across space and time. They link the violent deaths of massive stars to the quiet precision of cosmic timekeeping, serving as both reminders of stellar destruction and tools for exploring the universe's deepest mysteries. From here, our journey will take us into the realm of even stranger neutron star variants, stars whose magnetic fields push the limits of physics and whose outbursts can outshine galaxies. The Magnetars. Magnetars. If pulsars are the precise ticking clocks of the cosmos, magnetars are the universe's roaring, unpredictable thunderclaps. Rare, volatile neutron stars whose magnetic fields are so unimaginably strong that they defy comprehension. With magnetic strengths up to 1,000 trillion times that of Earth, magnetars are the most magnetic objects known in the universe. Their power is so intense that it can twist their crusts, tear apart nearby molecules, and release energy bursts that momentarily outshine entire galaxies. A magnetar begins its life much like any other neutron star, born in the aftermath of a supernova explosion. The difference lies in the conditions of its birth. For reasons still not fully understood, a small fraction, perhaps less than 1 in 10, of newborn neutron stars acquire these staggering magnetic fields. One leading theory suggests that if the core of the collapsing star spins unusually fast, combined with turbulent convection, during the collapse, a dynamo effect amplifies the magnetic field to extraordinary strengths, before the young neutron star settles into its final form. The result is a stellar remnant with a magnetic field strong enough to distort the very shape of atoms, stretching them into needle-like forms. The most dramatic hallmark of magnetars is their ability to produce giant flares, immense explosions of energy released when their magnetic fields shift or decay. In December 2004, one such flare from a magnetar known as SGR 180-6-20 released more energy in a fraction of a second than the Sun produces in 150,000 years. Even from its distance of about 50,000 light-years, the blast momentarily affected Earth's upper atmosphere and saturated detectors on satellites designed to observe gamma rays. Had this magnetar been within 10 light-years, it might have stripped away our planet's ozone layer, with devastating consequences for life. Magnetars are classified into two main observational groups: soft gamma repeaters, SGRS, and anomalous X-ray pulsars, AXPS. Despite their names, both are believed to be manifestations of the same underlying object. SGRs are so named because they emit repeated bursts of soft gamma rays and X-rays, often during active periods that can last weeks or months. AXPs, on the other hand, are persistent X-ray sources that occasionally produce outbursts. The distinction is largely historical, dating from a time when their connection was not yet understood. Today we know that the differences likely stem from variations in viewing angle, magnetic field geometry, or activity stage. The magnetar's magnetic field is not just a passive property. It actively shapes the star's evolution. Over thousands of years, these magnetic fields gradually decay, releasing heat that keeps the surface unusually warm for a neutron star of its age. This decay also powers the star's persistent X-ray emissions, which can be millions of times brighter than what we would expect from a cooling neutron star alone. When stresses from the shifting magnetic field become too great, the crust can fracture in a starquake, unleashing a sudden burst of high-energy radiation. The physics inside a magnetar is an active area of research, much of it pushing the boundaries of quantum electrodynamics. The magnetic fields are so strong that they can cause vacuum birefringence, a predicted effect where even empty space behaves like a prism, bending and polarizing light. This phenomenon has been tentatively observed in a few neutron stars and may be more pronounced in magnetars, offering a potential observational signature to confirm the theory. Magnetars also have unusually slow rotation rates compared to many pulsars, typically spinning once every 2 to 10 seconds. This is because their intense magnetic fields create powerful magnetic braking, slowing their rotation over relatively short timescales. In fact, their rotational energy is not the primary driver of their emissions. Their magnetic energy is. This makes them fundamentally different from rotation-powered pulsars, whose beams are fueled by their spin. Despite their rarity, only about 30 confirmed magnetars are known. They have an outsized impact on astrophysics. Some fast radio bursts, FRBs, mysterious millisecond-long flashes of radio waves from distant galaxies, are thought to originate from magnetar activity. In 2020, astronomers detected an FRB from within our own galaxy for the first time, traced to a magnetar designated SGR 1935+2154. This discovery strengthened the link between magnetars and at least some FRBs, though the full picture is still emerging. Their potential role in other cosmic phenomena is equally intriguing. In some superluminous supernovae, explosions dozens of times brighter than typical supernovae, the extra energy may come from a newborn magnetar injecting rotational and magnetic energy into the expanding debris. In gamma-ray bursts, particularly the long-duration type associated with massive star collapses, a rapidly spinning magnetar may act as a central engine, driving powerful jets into space. Observing magnetars is challenging because of their sporadic and unpredictable activity. Many remain quiet for years before suddenly entering an active phase, producing bursts and flares that can be detected across the electromagnetic spectrum. Space telescopes like NASA's SWIFT and ESA's XMM Newton play a crucial role in catching these events, often triggering follow-up observations from ground-based radio and optical telescopes. The transient nature of magnetars means that each detection is a valuable opportunity to study physics in one of the most extreme environments in the universe. Magnetars also have an almost mythic quality in the minds of astronomers. They are the ultimate expression of stellar magnetism, where the familiar concept of a magnetic field becomes something alien and dangerous. To stand anywhere near one would be impossible, not only because of the crushing gravity, but because its magnetic field could scramble the electrons in your atoms, tearing you apart at the subatomic level. This is not science fiction. It is the logical consequence of physics at these scales. Their magnetic dominance also extends far beyond their immediate surroundings. A magnetar's field can interact with the interstellar medium, potentially influencing nearby clouds of gas and dust. In theory, the magnetic pressure from a highly active magnetar could even suppress star formation locally. Though given their rarity and short active lifespans, typically only about 10,000 years, this effect would be highly localized in both space and time. Still, it underscores the point that magnetars are not just isolated curiosities. They can have tangible impacts on their environments. The decay of their magnetic fields is a slow but powerful process. As the magnetic energy dissipates, it generates heat, which leaks to the surface and radiates into space as X-rays. This energy budget is so immense that even after thousands of years, magnetars remain brighter than ordinary neutron stars of the same age. Eventually, as their magnetic fields weaken, magnetars will fade into more typical neutron stars, becoming indistinguishable from other members of that class. But during their prime, they are astrophysical fireworks, brilliant, dangerous, and utterly unique. Some magnetars have provided unexpected surprises. For instance, the Magnetar X TEJ 1810-197 was the first to be observed emitting pulsed radio waves, something long thought impossible for magnetars. This discovery blurred the boundaries between pulsars and magnetars, suggesting that under certain conditions, a magnetar's magnetosphere can support radio emission similar to that of pulsars. Since then, a handful of other radio-emitting magnetars have been found, revealing that these objects may be more diverse than we originally believed. Another area of active research involves the connection between magnetars and gravitational waves. While no gravitational waves have yet been directly linked to a magnetar event, starquakes and magnetic field reconfigurations could, in theory, produce ripples in space-time detectable by sensitive observatories like LIGO and Virgo. If such a detection were made, it would open a new window into magnetar interiors, allowing scientists to probe their structure through entirely different physics. The study of magnetars is also tightly linked to the investigation of extreme matter states. The pressures and densities in their interiors, coupled with their ultra-strong magnetic fields, may give rise to exotic particle interactions. Some models predict that the core of a magnetar could contain hyperons, particles containing strange quarks, or even more exotic condensates. The interplay between the magnetic field and this dense matter is poorly understood, but is likely to influence everything from the star's stability to the exact shape of its magnetic decay curve over time. From an observational standpoint, one of the most fascinating aspects of magnetars is their unpredictability. While pulsars can be relied upon to tick away with precision, magnetars can go silent without warning or erupt in violent flares with little prior indication. For astronomers, this means constant vigilance and rapid response capabilities are essential. Modern astronomy's global network of telescopes and satellites enables a coordinated chase whenever a magnetar wakes up, capturing its emissions across multiple wavelengths before it fades again. Even in their quiet phases, magnetars are worth studying. Their persistent X-ray emissions carry information about their surface composition, the structure of their crust, and the residual heat from both their birth and their ongoing magnetic decay. High-resolution spectroscopy of this light can reveal spectral lines subtly shifted by gravitational redshift, offering another method for measuring the star's mass and radius, key parameters in determining the equation of state for dense matter. The rarity of magnetars might suggest that they are astrophysical oddities with limited relevance to the broader universe. But the opposite is true. Their extreme conditions make them natural laboratories for testing fundamental physics in ways no terrestrial experiment can match. By pushing matter, magnetism, and gravity to their limits, Magnetars illuminate the boundaries of our physical theories, showing us where those theories succeed and where they may break down. Quark stars and strange stars. When neutron stars were first theorized, they already seemed like the ultimate expression of matter under pressure, a city-sized sphere of neutrons packed so tightly that a teaspoon would weigh 1 billion tons. But what if nature could compress matter even further, breaking apart the neutrons themselves into their constituent quarks? This question leads us into the realm of quark stars and strange stars, hypothetical objects that could exist beyond the limits of conventional neutron star physics. Quarks are the fundamental building blocks of protons and neutrons, bound together by the strong nuclear force. In normal matter, quarks are confined within these particles, never existing freely due to a phenomenon known as color confinement. However, at extreme densities and pressures, conditions far surpassing those in atomic nuclei, it's possible that neutrons could melt into a soup of unbound quarks. This exotic state of matter is called quark-gluon plasma, a fluid of quarks and gluons free to move within a larger volume. Quark stars, if they exist, would form when a neutron star's core reaches densities high enough to force this phase transition. Instead of a core made purely of neutrons, the star would consist entirely of deconfined quark matter. This would make it even denser than a neutron star, with an equation of state that allows it to shrink to a smaller radius for the same mass. The differences might be subtle from the outside. Both neutron stars and quark stars would have extreme gravity and similar appearances, but the physics inside would be radically different. One fascinating subset of this idea is the strange star. In particle physics, there are 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom. Ordinary matter is built from up and down quarks, but in extreme conditions, strange quarks can appear. If strange quarks are stable under such pressures, they might mix with up and down quarks to form what is known as strange quark matter. A strange star would be made almost entirely of this exotic material, and some theories suggest that strange matter could be the most stable form of matter in the universe. This leads to an astonishing implication. If a piece of strange matter, called a strangelay, were to come into contact with normal matter, it might convert it into more strange matter. This strange matter contagion scenario is highly speculative, and there's no evidence it has ever happened. But it's an idea that has captured the imagination of physicists and science fiction writers alike. In principle, if strange matter is indeed more stable, then once it forms, it could spread, though real astrophysical conditions might prevent such runaway conversion from occurring in practice. Detecting quark or strange stars poses a major observational challenge. Because their surfaces and masses could be very similar to neutron stars, astronomers must look for more subtle clues. One possible indicator is an unusually small radius for a given mass, measurable through X-ray observations of hotspots on the surface. Another is unusually fast cooling rates, as quark matter could conduct heat differently from neutron matter. The detection of certain gravitational wave signals from neutron star mergers might also provide indirect evidence, as the equation of state of quark matter could leave a unique imprint on the merger waveform. There are a few candidates for quark or strange stars in the astronomical record. One example is the compact object RxJ 185.6.5-3754, a nearby isolated neutron star whose radius and temperature measurements have led some to speculate about a quark star interior. Another candidate is the pulsar PSRJ 1614-2230, which has a mass close to the theoretical maximum for neutron stars. If its radius is smaller than expected, it might hint at exotic matter inside. However, these identifications remain highly uncertain, and most can still be explained by variations in neutron star physics without invoking quark matter. The existence of quark stars would have profound implications for our understanding of matter. If strange quark matter is indeed the most stable state, it could mean that ordinary nuclear matter is only metastable, a temporary phase in the cosmic energy landscape. The universe might be littered with tiny strangelays, remnants of high-energy processes in the early universe, or in the violent collisions of compact stars. Some have even speculated that such strangelets could be detectable as unusual cosmic rays hitting Earth's atmosphere, though no confirmed detection has been made. Quark stars also connect directly to laboratory physics at facilities like the Large Hadron Collider, LHC, and the Relativistic Heavy Ion Collider, RHIC. Scientists create fleeting droplets of quark-gluon plasma by smashing heavy ions together at near-light speeds. These droplets exist for mere trillionths of a second before cooling back into normal matter, but they offer a glimpse into the conditions that might prevail inside a quark star. By comparing experimental data with astrophysical models, researchers can constrain the possible behaviors of quark matter at astronomical densities. In terms of appearance, quark and strange stars could differ from neutron stars in intriguing ways. For instance, they might have a bare quark surface without a traditional crust, allowing photons to escape more directly and giving them a harder spectrum. Alternatively, they could have a thin nuclear crust suspended above the quark matter by electrostatic forces, a bizarre arrangement unlike anything seen in ordinary stars. Their magnetic fields might also behave differently, influencing how they spin down over time. Another way quark and strange stars might reveal themselves is through catastrophic astrophysical events. When two neutron stars merge, the resulting remnant is subjected to immense pressures and temperatures. In some scenarios, this could trigger the conversion of neutron matter into quark matter, either in the core or throughout the entire star. If such a phase transition occurs, it might produce a distinctive secondary signal in gravitational waves, a brief aftershock of space-time ripples, as well as a unique pattern in the electromagnetic emission from the merger. Future high-sensitivity gravitational wave observatories could look for exactly these fingerprints. Some theorists have even proposed that certain short gamma-ray bursts could be powered by the formation of a quark star. In these models, the initial burst of gamma rays is followed by a plateau in brightness caused by the stable spin-down of a newborn quark star. The exact details depend heavily on the physics of dense matter, but these scenarios offer testable predictions for astronomers. The early universe also provides a potential laboratory for strange matter. Just fractions of a second after the Big Bang, the cosmos was a hot, dense soup of quarks and gluons, not yet locked into protons and neutrons. If strange quark matter formed during this era and was stable, some of it might have survived to the present day as strangelets, drifting through interstellar space. If they exist, strangelets could occasionally pass through Earth, depositing tiny but measurable energy as they interact with our atmosphere or solid detectors. Experiments such as cosmic ray observatories and deep underground particle detectors have searched for such events, but no confirmed detections have yet occurred. Another fascinating aspect of quark and strange stars is their possible role in the mass gap problem. Observations of compact objects suggest a scarcity of masses between the heaviest neutron stars, around 2.3 solar masses, and the lightest known black holes, around 5 solar masses. If quark stars exist, they might fill part of this gap, existing stably at masses above the maximum for neutron stars but below the threshold for collapse into a black hole. Confirming this would not only expand the known family of compact objects, but also provide a missing link in stellar evolution. From a structural standpoint, quark and strange stars would be the ultimate in compactness short of a black hole. Their surfaces would be extreme environments unlike anything in the known universe. In the bare surface model, the quark matter would be exposed directly to space, with an electric field at the boundary so intense that it could spontaneously produce electron-positron pairs. This could create a constant thin layer of radiation surrounding the star, potentially observable as an unusual emission spectrum. Even their cooling behavior would differ. Whereas neutron stars primarily lose heat via neutrino emission in the first million years, strange stars might cool more rapidly due to enhanced neutrino production channels within quark matter. This could make young strange stars appear colder than neutron stars of similar age, a subtle signature detectable with precise X-ray measurements. The scientific allure of quark and strange stars is partly due to their rarity. If they exist at all, they may be exceedingly uncommon, and partly because they represent a fundamental shift in our understanding of matter's stability. They would imply that the familiar protons and neutrons making up our world are not the true ground state of matter, but rather a temporary configuration. In this view, all normal matter is perched on a metastable plateau, with strange matter lying in a deeper, more stable valley. For now, Quark and strange stars remain tantalizing possibilities. They exist comfortably in the space between theory and observation, supported by plausible physics, but unconfirmed by direct evidence. As observational technology advances, especially in X-ray astronomy, gravitational wave detection, and high-energy astrophysics, we may find the smoking gun that reveals their existence. Until then, they serve as a reminder that the universe may hold forms of matter and types of stars we have yet to encounter, each stranger than the last. Carbon stars. Among the great variety of stars that dot our galaxy, there is a rare and beautiful class that stands apart, not because of their size or temperature, but because of their chemistry. These are the carbon stars, luminous giants whose outer layers are rich in carbon. They shine with a deep reddish hue that makes them some of the most visually striking stars in the sky. The source of this unusual composition lies in the complex processes that occur during the final stages of a star's life, when the slow but relentless march of stellar evolution brings fresh carbon from the core to the surface. Most stars, including our Sun, fuse hydrogen into helium for the majority of their lifetimes. As they age, the helium in their cores is fused into carbon and oxygen. In most cases, that carbon stays locked in the core and never reaches the surface. But in a carbon star, a process called dredge-up changes the equation. As the star swells into a red giant, convection currents in its outer layers dig deep into the interior, carrying freshly minted carbon from the core to the atmosphere. This shifts the balance of elements in the star's outer layers, making carbon more abundant than oxygen. This chemical change has a dramatic effect on the star's appearance. In a normal star, oxygen binds with carbon to form carbon monoxide, using up almost all the carbon. The leftover oxygen forms molecules like titanium oxide, which give red giants their characteristic orange-red color. But in a carbon star, the situation is reversed. Oxygen is the limiting ingredient. After carbon monoxide forms, leftover carbon combines into molecules such as C2 and CN. These molecules absorb blue and green light, allowing more red light to escape, and giving the star its deep crimson glow. Carbon stars are typically found on the asymptotic giant branch, a late stage in the life of low to intermediate mass stars. In this phase, they have exhausted the hydrogen and helium in their cores, and fusion occurs in shells around the core. The dredge-up events that enrich their surfaces in carbon often happen multiple times, each one increasing the carbon content. Eventually, the outer layers of the star are puffed out into space by stellar winds, creating beautiful shells of gas and dust. These winds carry carbon-rich material into the interstellar medium, where it can later contribute to the formation of new stars, planets, and even life. This role in cosmic recycling is one of the most important contributions carbon stars make to the galaxy. Carbon is a key ingredient for organic chemistry, and without stars like these, the universe would be far poorer in the element that forms the backbone of life. The carbon in your body was almost certainly forged in the cores of ancient stars, then spread through space by the winds of giants like these. Observationally, carbon stars have been known since the 19th century, when their unusually red colors and distinctive spectra set them apart from other stars. Spectroscopy, the study of light spread into its component colors, reveals their unique molecular bands, which act like fingerprints for the carbon-rich molecules in their atmospheres. In fact, these spectra are so distinctive that even an amateur astronomer with a small telescope and a spectroscope can confirm the carbon-rich nature of a bright example. Some carbon stars are even visible to the naked eye under dark skies, appearing as tiny ruby sparks among the constellations. One of the most famous is a star nicknamed La Superba in the constellation Canes Venatici. This name, meaning the superb one, comes from its vivid red color, which impressed 19th century observers. At around 600 light-years away, it is close enough for its details to be studied in depth, making it a benchmark for understanding the class. Carbon stars are divided into several subtypes, depending on how they acquired their carbon and other details of their composition. The classic carbon stars are intrinsic, meaning they produced their own carbon through fusion and brought it to the surface via dredge-up. Others are extrinsic, meaning they gain their carbon through interaction with a companion star. In such systems, the carbon-rich material was transferred from a companion that had already gone through its carbon-rich phase, leaving the recipient star chemically altered. These binary interactions can produce some unusual stellar relationships. In some cases, the companion star that donated the carbon has now evolved into a white dwarf, a faint, Earth-sized stellar remnant that is difficult to detect directly. But its past influence is written clearly in the spectrum of its partner, which now glows with the signature of carbon molecules. These so-called CH stars and barium stars are examples of how close stellar partnerships can leave lasting chemical fingerprints. The life of a carbon star is not just about slow chemical enrichment. It is also about powerful winds and mass loss. In the final stages, the star's outer layers become unstable, pulsating in size and brightness over periods of hundreds of days. These pulsations, combined with radiation pressure on dust grains, drive vast amounts of material into space. Observations in the infrared reveal thick shells of dust around many carbon stars, glowing with the heat of the starlight they absorb. This dust often contains solid carbon in the form of graphite or even microscopic diamonds, grains that will drift through the galaxy for millions of years. The dust shells of carbon stars are not just chemically interesting, they are also visually stunning when imaged with modern telescopes. In some cases, these shells appear as concentric rings, marking episodes of enhanced mass loss. In others, the dust is shaped into spirals by the gravitational influence of a companion star, producing patterns that are both scientifically revealing and aesthetically beautiful. Astronomers study these structures not only to learn about the stars themselves, but also to understand the flow of matter through the galaxy. Every carbon star eventually sheds much of its mass into space, enriching the interstellar medium and influencing the next generation of stars and planets. This slow redistribution of elements is part of the cosmic cycle that links the lives of stars to the chemistry of planets and living things. In addition to their beauty, carbon stars play an important role in understanding stellar evolution. Because they are in a late evolutionary phase, they give astronomers a window into the processes that occur after a star has exhausted the hydrogen and helium in its core. Observations of carbon stars help refine models of mass loss, pulsations, and chemical mixing, processes that are challenging to study in other types of stars. By comparing their observed properties to computer simulations, scientists can better predict how stars like our Sun will evolve in billions of years. One fascinating aspect of carbon stars is how their brightness changes over time. Many are classified as long-period variables, meaning their light output fluctuates in cycles that can last several hundred days. The changes are caused by the rhythmic expansion and contraction of the star's outer layers. During these cycles, the temperature and size of the star change enough to affect its color and brightness noticeably. This variability adds to their allure for amateur and professional astronomers alike, as a single star can look subtly different from one season to the next. Infrared astronomy has been especially valuable in studying carbon stars, because much of the light they emit is absorbed and re-radiated by the dust surrounding them. They often appear brighter in infrared than in visible light. Space telescopes such as the Infrared Astronomical Satellite and the Spitzer Space Telescope have mapped hundreds of carbon stars in our galaxy, revealing details about their dust shells, mass loss rates, and overall contributions to the galactic ecosystem. More recently, the James Webb Space Telescope has been used to study the complex molecular chemistry in these dusty envelopes, finding a rich variety of carbon-based compounds. Some carbon stars are extreme enough to be called supercarbon stars, with carbon-to-oxygen ratios far higher than average. These stars have particularly thick and opaque dust shells, making them almost invisible in visible light. Observing them requires infrared or even radio wavelengths, where the dust becomes transparent. These heavily enshrouded stars are thought to be in the final phases before shedding their envelopes entirely and becoming planetary nebulae. In those future nebulae, The carbon-rich gas will mix with the surrounding interstellar medium, leaving behind intricate clouds glowing in shades of red, blue, and green. There is also a connection between carbon stars and the origin of certain types of meteorites found on Earth. Some meteorites contain microscopic grains of graphite and silicon carbide that have isotopic signatures matching what we expect from carbon star outflows. These pre-solar grains are tiny time capsules from before the sun was born, having traveled through interstellar space for billions of years before becoming part of the solar system. In this way, studying carbon stars is not just about understanding distant points of light. It is also about tracing the history of the matter that eventually formed our own planet. The future of carbon star research is bright, especially with new observatories coming online. Next-generation infrared telescopes on Earth will be able to study their dust shells in greater detail, while space missions will search for carbon stars in other galaxies, comparing their properties to those in the Milky Way. By studying these stars across different galactic environments, astronomers hope to learn how metallicity, the abundance of elements heavier than hydrogen and helium, affects the formation and evolution of carbon stars. Ultimately, carbon stars are reminders that the life cycles of stars are deeply connected to the existence of life itself. Without them and other stellar factories of carbon, the universe would be a far less interesting place, devoid of the complex molecules that make planets, plants, and people possible. Each glowing red giant is both an endpoint and a beginning, the end of a star's main sequence life, and the beginning of a new chapter in the story of cosmic chemistry. Rayet stars. Among all the stars that shine in our galaxy, few are as fierce, as short-lived, and as utterly extreme as the Rayet stars. These are not the quiet, steady burners like our sun, nor the dense remnants like Neutron Stars. Rayet stars are giants in the prime of their fury, burning through their nuclear fuel at a breakneck pace and stripping away their own outer layers in titanic stellar winds. They live fast, die young, and in their brief lives, they change the chemical balance of entire regions of space. The story of these stars begins in the year 1867, when French astronomers Charles Wolf and Georges Rayet were examining the spectrum of certain stars in the constellation Cygnus. They noticed something unusual. Instead of the thin, dark absorption lines seen in most stellar spectra, these stars showed broad, bright emission lines, as if they were glowing from vast clouds of heated gas surrounding them. At the time, this was a mystery. Nobody knew what kind of star could produce such a spectrum. It would take decades for astronomers to piece together the puzzle and realize that these stars were in a rare, late stage of evolution, exposing their hot, inner layers to space. Rayet stars are extremely hot, with surface temperatures that can start around 25,000 degrees Celsius and rise to well over 200,000. They are so hot that they pour out most of their light in the ultraviolet part of the spectrum, invisible to human eyes. In visible light, they often appear bluish-white, sometimes tinged with a faint purple hue due to the blending of high-energy emissions. But what really sets them apart is not just their temperature, it is the ferocity of their stellar winds. These winds are not gentle breezes. They are hurricane-force outflows on a scale almost impossible to imagine. A Rayet star can lose the mass of Earth every few days, blowing it away into space at speeds up to 3,000 kilometers per second. Over the few 100,000 years that they exist in this phase, they can shed several times the mass of our sun. This constant shedding exposes the deeper layers of the star, revealing the products of nuclear fusion that normally remain hidden inside. The chemistry of a Rayet star's surface depends on which stage of nuclear fusion is currently exposed. Some are rich in helium and nitrogen, showing that hydrogen fusion has long since ended, and the star's core has been reprocessed through the CNO cycle. These are called nitrogen sequence Rayet stars. Others are rich in carbon and oxygen, showing the byproducts of helium fusion. These are the carbon sequence Rayet stars. There is also a smaller, rarer group that shows oxygen dominance, the oxygen sequence Rayet stars. The life cycle of such a star is a race against time. Rayet stars are born from the most massive main sequence stars, usually with more than 20 times the mass of the Sun. Their immense mass causes them to burn through their hydrogen fuel incredibly quickly, often in just a few million years, When the hydrogen is gone, they swell into supergiants, and eventually, strong stellar winds strip away their hydrogen envelope entirely. This stripping can be driven by their own radiation pressure, or accelerated by the gravitational tug of a close companion star. What is left is a naked core, blazing hot and unstable. This is the Wolf-Rayet stage. One of the most dramatic consequences of these winds is the creation of intricate nebulae. As the outflow slams into surrounding gas, it carves out vast glowing shells and bubbles. The Crescent Nebula in Cygnus is a perfect example, formed by the winds of a central Wolf-Rayet star, colliding with material it ejected earlier in its life. These bubbles are not static. They expand over tens of thousands of years, eventually dispersing into the interstellar medium, where their enriched material becomes part of new generations of stars and planets. Wolf-Rayet stars are incredibly rare. In a galaxy of hundreds of billions of stars, only a few hundred Wolf-Rayet stars are known. This rarity is partly because they form only from the most massive stars, and partly because the Wolf-Rayet phase is so short-lived. Catching a star in this stage is like seeing a firework at the exact moment of its brightest burst. It is fleeting on cosmic timescales. The fate of a Wolf-Rayet star is almost always explosive. Many will end their lives as stripped envelope supernovae. Supernovae of type Ib or IC, where almost all of the hydrogen and often much of the helium has been lost before the final collapse. In these explosions, the core collapses into either a neutron star or a black hole, while the outer layers are hurled into space at thousands of kilometers per second. The shockwave and debris enrich the galaxy with heavy elements, particularly carbon, oxygen, and neon. In some extraordinary cases, a Wolf-Rayet star's death may produce one of the most energetic events in the universe, a long-duration gamma-ray burst. For this to happen, the star must be rapidly rotating at the time of collapse, and its core must form jets of material that punch through the star's outer layers at nearly the speed of light. These gamma-ray bursts can last from a few seconds to several minutes, releasing as much energy as the sun will produce over its entire 10 billion year lifespan. Wolf-Rayet stars are not always solitary. Many are found in binary systems, often paired with another massive star. In such systems, the strong winds from the Wolf-Rayet star collide with the winds from its companion, creating a region of shocked gas that can produce bright X-ray emission and even accelerate particles to near-light speeds. These colliding wind binaries are astrophysical laboratories for studying how massive stars interact and lose mass. Some of the most beautiful infrared and radio images in astronomy come from these interacting wind structures, which can form spirals, arcs, and complex bow shapes. Their role in the galaxy extends beyond their immediate surroundings. The elements they produce, carbon, oxygen, neon, are critical for the chemistry of life and for the cooling of interstellar gas clouds, which allows new stars to form. Without massive stars going through stages like the Wolf-Rayet phase, the universe would be far poorer in the elements that make planets, oceans, and living things possible. In this way, their short, violent lives have long-lasting consequences. From an observational perspective, finding and studying Wolf-Rayet stars is challenging. Their ultraviolet-dominated spectra mean they are often best studied with space-based telescopes that can see beyond the range of human vision. In optical light, their emission lines are the giveaway, broad features produced by the high-speed motion of their winds. Infrared observations are particularly useful for finding them through the dust that often surrounds them, and radio observations can reveal the structure of their wind-blown shells. In some regions of our galaxy, Wolf-Rayet stars appear in clusters, often near the dense star-forming cores where massive stars are born. This makes sense, since they originate from the largest and hottest young stars. These stellar nurseries are rich in gas and dust, and the presence of Wolf-Rayet stars can dramatically alter their environments. Their intense ultraviolet light ionizes surrounding hydrogen, creating large glowing regions known as H2 regions. Their winds sweep up and compress the surrounding gas, sometimes triggering the birth of new stars, while at the same time eroding the raw material for future generations. One of the most famous examples of such a cluster is the quintuplet cluster near the center of the Milky Way, which contains multiple Wolf-Rayet stars, along with other massive, luminous giants. Observations of this cluster reveal the turbulent life of such regions. The interplay of gravity pulling stars together, radiation pushing gas away, and winds shaping everything into arcs and filaments. It is in such chaotic places that the seeds of both creation and destruction are sown, driven in part by the restless lives of Wolf-Rayet stars. The diversity within the Wolf-Rayet family is also worth noting. Nitrogen-sequence Wolf-Rayet stars show strong lines of ionized nitrogen and helium, indicating that the hydrogen-burning products have been brought to the surface. These stars are often earlier in the Wolf-Rayet phase and still have some helium layers intact. Carbon-sequence Wolf-Rayet stars, on the other hand, display prominent carbon and helium lines, marking a later stage where helium fusion products dominate. Oxygen-sequence Wolf-Rayet stars are the rarest, showing significant oxygen enrichment, a sign that the star is nearing the end of its evolution before collapse. Not all Wolf-Rayet stars form from single massive stars. In binary systems, mass transfer can strip a star's outer layers long before stellar winds alone could accomplish it. In such cases, a star that might never have been massive enough to become a Wolf-Rayet star on its own can be transformed into one through the intervention of its companion. These binary interactions add complexity to our understanding of stellar evolution, as they can create Wolf-Rayet stars from stars with much lower initial masses than previously thought. The winds from Wolf-Rayet stars are also a puzzle for astrophysicists. While we know they are driven by radiation pressure on atoms and ions in the star's outer layers, the exact details of how these winds are accelerated to such extreme speeds are still being refined. The winds are not smooth, but clumpy, with dense blobs of material embedded in a more tenuous flow. These clumps affect the star's mass loss rate and, in turn, influence how it will evolve and die. Understanding the fine structure of these winds is an active area of research, as it ties directly into predictions about supernova types and gamma-ray burst progenitors. Wolf-Rayet stars are not confined to our galaxy. They are found in many others, particularly in galaxies with high rates of star formation. The Large Magellanic Cloud and the Small Magellanic Cloud, two of our Milky Way's satellite galaxies, contain dozens of Wolf-Rayet stars. Studying these stars in different galactic environments helps astronomers understand how metallicity, the abundance of elements heavier than helium, affects stellar winds and evolution. In galaxies with lower metallicity, stellar winds are generally weaker, which can alter the duration of the Wolf-Rayet phase and the types of explosions these stars eventually produce. As they approach the end of their lives, Wolf-Rayet stars can experience dramatic changes in brightness, sometimes erupting in outbursts that temporarily increase their luminosity. These events may be linked to instabilities in their outer layers or sudden changes in wind structure. Some stars oscillate between the Wolf-Rayet phase and a luminous blue variable phase, shedding enormous amounts of mass in each transition. These late-life spasms can set the stage for unusual types of supernovae, including some of the most energetic and luminous ever observed. From a human perspective, the timescales of these changes are still long, decades or centuries, but in cosmic terms, they happen in the blink of an eye. The Wolf-Rayet phase itself is fleeting compared to the overall lifespan of a star, lasting only a few 100,000 years at most. Once the core's fuel is exhausted and the final collapse begins, the transformation is swift. Whether they go out as a brilliant supernova or vanish into a black hole without a visible explosion, their departure leaves behind a changed environment, enriched with the raw materials for the next generation of cosmic structures. In many ways, Wolf-Rayet stars are like cosmic sculptors. They shape their surroundings with winds, floods of ultraviolet light, and their final explosions. They are both destroyers and creators, destroyers of their own mass and of nearby fragile gas clouds, yet creators of the heavy elements and shock waves that help form new stars and planets. Without them, the galaxy would be a far less dynamic and far less chemically diverse place. Blue stragglers. In the quiet order of a star cluster, every star is expected to follow the same general life path. They are born together, share the same age, and are made of the same chemical material. Over time, the most massive stars burn out first, moving off the main sequence into the realm of red giants, while smaller stars linger for billions of years. This pattern is so regular that astronomers can predict the stage of each star simply by knowing the age of the cluster. Yet, within this predictable cosmic order, there exists a small group of stars that seem to rebel against the rules. These are the blue stragglers, stars that, by all rights, should be aging gracefully into cooler, redder giants, but instead burn hot and blue, as if they were still in the prime of youth. Blue stragglers were first identified in the 1950s, when astronomers studying the globular cluster Messier 3 noticed something peculiar in its color magnitude diagram. A handful of stars sat above and to the left of the main sequence turnoff point, the location where stars of a given age begin to leave the main sequence. These stars were hotter and more luminous than the rest of the stars in the cluster, suggesting that they were more massive and therefore younger than the cluster's expected age allowed. At first, this seemed impossible. Star clusters form from the same gas cloud in a relatively short burst of star formation, so all their stars should be roughly the same age. How could some stars appear younger than their siblings? The key to the mystery lies in understanding what determines a star's lifetime. A star's mass dictates how quickly it burns through its hydrogen fuel. Massive stars are brighter, hotter, and shorter-lived, while smaller stars live much longer. In an old cluster, the most massive stars have already exhausted their hydrogen and evolved into red giants or collapsed into white dwarfs, neutron stars, or black holes. The main sequence turnoff point marks the mass threshold where stars are just finishing their main sequence lifetimes. Any star more massive than this threshold should no longer be on the main sequence, yet blue stragglers are. The leading theory for their existence is that blue stragglers are not truly young, but rather old stars that have gained new life through interactions with other stars. In dense environments like globular clusters, close encounters between stars are not only possible, but relatively common. Two stars can collide or merge into a single, more massive star. This merger star contains more hydrogen fuel in its core and can burn hotter and bluer than either of its progenitors, making it appear younger than the cluster's other stars. Another path to becoming a blue straggler involves binary star systems. In a close binary, one star may evolve into a giant and begin transferring mass to its companion. The recipient star gains mass and can rejuvenate, effectively resetting its evolutionary clock. This process, called mass transfer, does not require a full collision but can still produce a star that is hotter, brighter, and bluer than expected for its age. In some cases, the donor star may lose so much material that it becomes a white dwarf, leaving its once smaller companion to shine as a blue straggler. Astronomers now believe that both processes, collisions and mass transfer, can produce blue stragglers, but the dominant mechanism depends on the environment. In the crowded cores of globular clusters, where stars are packed tightly together, collisions and mergers may be the main source. In sparser open clusters, where direct collisions are rare, binary mass transfer is more likely to be responsible. These theories are supported by observations. In globular clusters, blue stragglers tend to be more common in the central regions, where stellar densities are highest and collisions are most frequent. In open clusters, blue stragglers are often found in binary systems, and their properties suggest they have undergone mass transfer. Spectroscopic studies have also revealed chemical signatures consistent with these formation pathways, such as unusual ratios of carbon and nitrogen, that indicate the star's surface has been polluted by nuclear-processed material from a companion. The rotational speeds of blue stragglers provide additional clues. A merger between two stars is expected to produce a rapidly rotating star, as angular momentum from the two progenitors is conserved in the combined star. Some blue stragglers indeed spin faster than normal stars of similar type. However, over time, magnetic braking, where a star's magnetic field carries away angular momentum through its stellar wind, can slow this rotation, masking the star's turbulent past. This means that while rotation can point to a recent merger, its absence does not rule one out. The mystery of blue stragglers deepens when we consider their long-term evolution. These stars will eventually leave the main sequence and evolve into giants, just like other stars of similar mass. But their origins may influence the details of this evolution. For example, a blue straggler formed through mass transfer might retain a binary companion, affecting how it loses mass in its giant phase. A merger product, on the other hand, may be more homogeneous in composition, influencing how it burns its remaining fuel. Blue stragglers are not limited to clusters. They have been identified in the galactic field, the general population of stars outside clusters, as well. These field blue stragglers likely formed through binary mass transfer, since stellar collisions are extremely unlikely in the relatively empty space between stars. Their existence in the field suggests that the processes that create blue stragglers are not restricted to dense stellar environments, but can operate wherever binary stars are found. The distribution of blue stragglers within star clusters offers even more insight into their nature. In many globular clusters, they are found in two distinct populations, one concentrated near the dense core and another spread throughout the outer regions. This bimodal distribution hints at multiple formation channels at work simultaneously. The core population is likely dominated by stars created through direct collisions and mergers, where gravitational interactions are intense. The outer population may form mainly through binary evolution, where stable pairs can interact and exchange mass over long periods without being disrupted by nearby stars. This dual origin is further supported by computer simulations of stellar dynamics. In these models, when stars are packed closely together, sometimes with tens of thousands of stars in a single cubic light year, the chance of physical collisions increases dramatically. Over millions of years, such encounters can produce enough merger products to explain the core population of blue stragglers. Meanwhile, the less crowded outskirts allow binary systems to survive undisturbed, slowly transferring mass from one star to the other, and creating blue stragglers in a much gentler way. One of the enduring challenges in studying blue stragglers is determining exactly when they formed. Unlike a newborn star, which shines at a brightness directly tied to its age, a blue straggler's age cannot be inferred from its temperature and luminosity alone. A merger or mass transfer can happen at almost any point in a cluster's history. So, two blue stragglers in the same cluster could be vastly different in rejuvenation age, despite sharing the same true chronological age as the cluster itself. Astronomers try to work around this by studying the binary status of blue stragglers. Long-term radial velocity measurements, tracking the slight shifts in a star's spectral lines due to its motion, can reveal whether the star is part of a binary system and how close its companion is. In open clusters, a significant fraction of blue stragglers turn out to have white dwarf companions, a strong indicator that they were formed through mass transfer. In globular clusters, fewer blue stragglers appear to be in binaries, consistent with the idea that many formed from single-star collisions and mergers. Some blue stragglers are even found with planetary systems, though this is rare. If a planet were present before the formation of a blue straggler, the violent processes of mass transfer or merger could easily disrupt or destroy it. Finding planets around blue stragglers raises intriguing questions about planetary survival and formation in such chaotic environments. Could some planets form after the blue straggler's creation, perhaps from disks of material shed during the merger process? This remains an open question. Another fascinating aspect is how blue stragglers influence the overall evolution of a star cluster. These rejuvenated stars are often among the most luminous main sequence stars in their clusters, and their mass means they can exert a stronger gravitational pull on surrounding stars. This can subtly alter the dynamics of the cluster, especially in its core, where the most massive stars tend to sink toward the center through a process called mass segregation. In this way, blue stragglers can contribute to the dense central concentrations seen in many old clusters. From an observational standpoint, identifying blue stragglers is relatively straightforward in well-studied clusters. Astronomers create a color magnitude diagram, plot the main sequence turn-off point, and look for outliers above and to the left, hotter and brighter than expected for their age. But interpretation is more complex. Some stars can mimic the appearance of blue stragglers due to measurement errors, unresolved binaries, or peculiar chemical compositions. Careful spectroscopic and photometric follow-up is essential to confirm their nature. As our telescopes improve, particularly in the ultraviolet and blue parts of the spectrum, astronomers can detect even fainter and more distant blue stragglers. Space-based observatories like the Hubble Space Telescope have been instrumental in finding blue stragglers in clusters far beyond our galaxy, in systems like the Large Magellanic Cloud. Studying these extragalactic examples allows scientists to test whether the same formation processes operate in different environments with different chemical compositions. What makes blue stragglers so compelling is not just their apparent defiance of stellar aging, but the way they embody the complex interplay between stellar evolution and stellar dynamics. They are living evidence that a star's life is not always a solitary, predetermined journey. It can be interrupted, altered, and renewed by encounters with others. In the cosmic dance of stars, these are the rejuvenated dancers who have found a way to keep moving to the music long after their peers have slowed. Thorne Żytkow objects. In the grand catalog of strange and exotic stars, there is one idea that sounds so unlikely, so counterintuitive, that it almost feels like it belongs in science fiction rather than astrophysics. Yet it is a real, scientifically supported possibility. It is called the Thorne Żytkow object, named after the two astrophysicists who first described it, Kip Thorne and Anna Żytkow, in the mid-1970s. Imagine for a moment a massive red supergiant star, one of the largest types of stars in the universe, so swollen that its outer layers could engulf the orbit of Jupiter. Now, picture, buried deep inside its bloated heart, a dense, city-sized neutron star, an object so compact that a teaspoon of its matter would weigh billions of tons. That is the essence of a Thorne Żytkow object, a star inside a star. The concept is built on a fascinating scenario of stellar interaction. In space, stars are not always solitary. Many, perhaps most, form in pairs or larger groups. In a close binary system, the more massive star evolves faster, eventually exploding in a supernova and leaving behind a neutron star. The less massive companion, still on its journey through normal stellar evolution, continues burning its fuel. Over millions of years, this surviving star swells into a red supergiant, its outer layers expanding to enormous dimensions. In certain situations, the neutron star's orbit begins to decay, spiraling closer and closer to the bloated giant. This slow inward journey can be caused by tidal forces between the two bodies, or by interactions with the extended atmosphere of the giant star. Once the neutron star plunges into the outer layers of the red supergiant, a violent but oddly graceful process begins. Astronomers call this the common envelope phase. The neutron star does not simply fall straight to the center. Instead, it orbits inside the supergiant's envelope, plowing through its gas like a submarine moving through an ocean of plasma. As it moves, it transfers energy to the surrounding gas, heating and pushing it outward. The orbit shrinks as the neutron star loses energy, spiraling ever closer to the supergiant's core. This can take anywhere from months to thousands of years, depending on the masses, densities, and relative velocities involved. Eventually, the neutron star reaches the core of the red supergiant. At this point, one might expect a catastrophic collision or total disruption of the star. But the physics allows for something even stranger. The neutron star can survive the plunge intact, settling at the very center of the supergiant, surrounded by the core material and the vast convective layers of the giant star above it. The result is a hybrid object. One part is a degenerate stellar remnant with gravity so strong it warps space-time around it, and the other part is an active, bloated star, continuing nuclear fusion in its outer shells. The presence of the neutron star dramatically changes the environment at the center. In an ordinary red supergiant, the pressure and temperature in the core are set by the weight of the overlying layers. In a Thorne Żytkow object, the neutron star's extreme gravity compresses the surrounding material to even greater densities and heats it to even higher temperatures. This unique configuration creates conditions for nuclear reactions that do not occur in any other kind of star. The original models predicted the synthesis of certain rare isotopes, including unusual amounts of lithium, rubidium, and molybdenum, elements that are either destroyed in normal stellar fusion or produced only in trace amounts. From the outside, a Thorne Żytkow object would look remarkably like an ordinary red supergiant. It would have the same ruddy glow, the same enormous size, and roughly the same luminosity. The only way to tell them apart would be by looking closely at their spectra, the fingerprints of light that reveal which elements are present in a star's atmosphere. If a red supergiant shows unusually high abundances of those predicted rare elements, it could be a candidate for being a Thorne-Żytkow object. Detecting such signatures is easier said than done. Red supergiants have complex, turbulent atmospheres filled with convective cells larger than the orbit of Earth. These create broad and often messy spectral lines that can mask subtle chemical differences. On top of that, the predicted elemental enhancements in a Thorne-Żytkow object are not enormous. They are significant, but require careful, high-resolution spectroscopy to identify. It is like trying to pick out the faint scent of a rare spice in a kitchen, already filled with dozens of strong aromas. The rarity of the conditions needed for their formation makes these objects elusive. You need a massive binary star system. You need one star to explode in a supernova without ejecting its companion. You need the surviving star to swell into a supergiant large enough to engulf the neutron star. And finally, you need the orbital mechanics to line up so that the neutron star spirals into the core rather than ejecting the envelope entirely. Each of these steps is uncommon. Together, they create an event that might occur only a handful of times in a galaxy at any given moment. Yet, the possibility is not just theoretical. In 2014, astronomers announced that they had found a star, HV 2112, in the Small Magellanic Cloud that showed the strange combination of elements predicted for a Thorne-Żytkow object. It displayed unusually high levels of lithium, rubidium, and molybdenum. While alternative explanations exist, such as a peculiar phase of stellar evolution or mass transfer in a binary, the object remains one of the most compelling candidates discovered so far. If HV 2112 or any other star like it is confirmed to be a Thorne-Żytkow object, it would not only validate decades of theoretical work, but also provide a living laboratory for studying extreme physics. We could learn more about how matter behaves under immense gravity and pressure, how unusual nuclear pathways operate, and how certain rare elements are forged and distributed in the galaxy. It would be a direct observational link between the life cycles of massive stars and the exotic end states they can produce. The life of a Thorne-Żytkow object after its formation is a balancing act between stability and inevitable change. For as long as the massive outer envelope of the red supergiant remains intact, the object can maintain its unusual internal configuration. Nuclear fusion in the outer layers continues, and the neutron star at the center exerts its intense gravitational influence, compressing the surrounding core material. This environment may persist for tens of thousands or even hundreds of thousands of years, a blink in cosmic terms, but still long enough for the object to leave its mark on the galaxy's chemical makeup. Over time, however, the star loses mass. Red supergiants have strong stellar winds, carrying away matter at rates thousands of times greater than our sun's. For a Thorne-Żytkow object, these winds may be even more intense due to the extra heat generated near the core. As the envelope thins, the pressure on the core decreases. Eventually, the balance can be broken, leading to one of several possible outcomes. In one scenario, the outer layers are completely lost before the core collapses. When this happens, the neutron star at the center is suddenly exposed, perhaps surrounded by a thin shell of hot plasma. The result could be a single neutron star with unusual properties. Or, in some cases, the collapse of the surrounding core material might push the neutron star over the mass limit for stability, turning it into a black hole. In another scenario, the Thorne-Żytkow object could end its life in a dramatic supernova-like explosion. If the envelope is still massive when the core reaches instability, the release of energy could eject the outer layers into space, enriching the surrounding interstellar medium with the rare elements that were forged inside. Such an event would be a powerful contributor to the galaxy's chemical evolution, scattering not just the common elements like carbon and oxygen, but also the rare isotopes unique to this stellar configuration. The influence of Thorne-Żytkow objects extends beyond their rarity. By producing and distributing elements like lithium and certain heavy isotopes, they may help explain abundance patterns observed in old stars and in the diffuse gas between stars. In this sense, they are part of the broader story of how the universe creates complexity over time. The material ejected by stars, whether in gentle winds or violent explosions, becomes the raw material for future generations of stars, planets, and potentially life itself. From an observational standpoint, confirming a Thorne Żytkow object requires both patience and precision. Astronomers must look for red supergiants in regions where massive binary systems are common, then obtain high-quality spectra to check for the telltale chemical signatures. Even then, caution is needed. Other stellar processes, such as unusual convection patterns or exotic phases of nuclear burning, can sometimes mimic these signatures. This means that no single chemical marker is definitive. Instead, scientists look for a consistent pattern across multiple elements, combined with other clues like stellar mass and luminosity. Space-based telescopes play an important role here. Observatories equipped to capture light in infrared and ultraviolet wavelengths can penetrate the dusty environments where red supergiants often reside. Since many Thorne Żytkow candidates could be partially hidden in star-forming regions or near the dense centers of galaxies, having access to multiple wavelengths greatly improves our chances of spotting them. In the future, instruments like the James Webb Space Telescope may provide the resolution and sensitivity needed to confirm or rule out candidates with much greater certainty than is possible today. The existence of these objects also invites us to think more broadly about the possible configurations of stars. For most of the history of astronomy, stars were seen as isolated spheres of gas, evolving in predictable ways based on their mass. But over the past few decades, it has become increasingly clear that interactions between stars are just as important as their individual properties. Binary and multiple star systems can exchange mass, alter each other's evolution, and in extreme cases, merge into exotic hybrids like the Thorne Żytkow object. One could even see these objects as a bridge between two very different categories of stellar phenomena. On one side are the massive, luminous giants like Betelgeuse, bloated and unstable in their final stages. On the other side are the compact remnants, neutron stars and black holes, that represent the dense, collapsed cores of dead stars. The Thorne Żytkow object is a union of both extremes, combining the vast, cool outer layers of a red supergiant with the tiny, ultra-dense core of a neutron star. As with many rare astronomical phenomena, our understanding of Thorne Żytkow objects is still in its infancy. We have a handful of strong candidates, solid theoretical models, and predictions that fit into the larger framework of stellar evolution. But direct, incontrovertible proof remains elusive. This is partly because of their short lifespans in astronomical terms, and partly because their outer appearance can so closely mimic that of ordinary red supergiants. If and when we finally confirm one beyond all doubt, it will be a triumph not just for the astrophysicists who first imagined it, but for the idea that the universe still holds surprises, combinations of matter and energy that push the boundaries of what we thought possible. Thorne Żytkow objects remind us that even in a cosmos governed by physical laws, nature can be inventive, finding unexpected ways to combine familiar ingredients into something entirely new. Hypergiants. If stars were legends, hypergiants would be the ones sung about in the grandest epics, too bright to ignore and too unstable to last. They are not merely large, they are extravagant. A hypergiant lives near the very edge of what a star can be, where the pressure of light itself pushes outward so strongly that the outer layers fight to stay bound. In that precarious balance, these stars glow with a brilliance that can outshine entire regions of their home galaxies. They burn through their fuel at a furious rate, breathe out colossal winds that reshape their neighborhoods, and end their lives in finales that spray heavy elements across space. Seen from afar, they can look serene, but up close they are storms of fire, light, and motion. A hypergiant begins life, like other very massive stars, in the dense heart of a cold cloud, where gravity wins a quiet battle against turbulence and heat. But the dice are loaded from the start. With dozens of times the mass of the sun, sometimes far more, the core pressure and temperature soar, and fusion proceeds at a pace that would tear a smaller star apart. The central fire pours energy outward. Deeper layers expand, contract, and expand again as the star seeks temporary balance. In that struggle, the surface becomes a restless sea. with waves the size of orbits and convection cells so large that our entire solar system could fall inside one and not touch the edges. To call these stars luminous is an understatement. Some radiate millions of times more energy than the sun. Their light pushes on the atoms in their outer layers, and that light pressure can be strong enough to lift material straight off the star. Imagine standing on a windy shore where the gusts are made of pure radiation. The air would not simply push your hair, it would lift the ocean into space. That is the reality on a hypergiant's surface. The result is a wind that flows at thousands of kilometers per second, carrying away mass in a continuous gale. Over a lifetime measured in only a few million years, a hypergiant can shed more mass than the sun will lose in 10 billion years. There is no single look that defines a hypergiant. Some are hot, blue-white, and piercing, with surfaces so hot that most of their light streams out in ultraviolet waves our eyes cannot see. Others are cool and swollen, glowing in gold or deep orange, with atmospheres that billow far beyond orbits where planets might be. A cool red hypergiant can grow so large that, if placed where the sun is, it could swallow Jupiter and still have room to spare. In both cases, the message is the same. Size and light are a double demand on the star's strength, and the star pays for them with instability. That instability comes in many forms. The interior layers are stacked like rings in a tree, each ring fusing a different fuel at a different temperature. Hydrogen burns to helium in a shell, helium burns to carbon in a deeper shell, and heavier elements form in layers still closer to the core. Each shell can pulse or flare. When they do, waves of pressure run through the star and crash at the surface, where the gravity is barely able to hold on. A wave that would be a harmless shiver in a smaller star becomes, in a hypergiant, a launch. Whole clumps of gas rise, cool, condense into dust, and sail away. Over time, these outflows build veils and lobes and shells that a telescope can see, expanding bubbles and hourglass shapes that tell a history of eruptions frozen in space. A famous example sits in a southern constellation, wrapped in a nebula that looks like a butterfly carved from smoke. In the 19th century, it brightened so dramatically that it rivaled the brightest stars in the sky, then faded again, leaving behind two thick lobes of gas called the Homunculus Nebula. That display was not a final death, but a warning. For a while, the star swelled with pride, sent its atmosphere outward in a flood, and then settled back, wounded but alive. Many hypergiants do this more than once. Some cycle between quieter phases and wild outbursts that can last years. During an outburst, the wind grows denser and heavier, and the star builds a mask of dust that hides its hottest light and sends a warm glow into the infrared. When the outburst ends, the wind thins and the mask begins to drift away. A slow-motion storm seen over decades. The chemistry in those drifting shells is not a footnote. As the gas cools, atoms latch onto one another and build grains of dust. Silicates, carbon compounds, and more complex structures forged in the breeze of a dying giant. These grains go on to seed other clouds where new stars will form. In this way, a hypergiant is both a destroyer and a gardener. It tears itself apart and, in doing so, enriches the soil of the galaxy with the material needed for planets, rocks, and in time, the molecules of life. Without such stars, a galaxy would be a poorer place, light but little complexity, bright but sterile. The lives of hypergiants are social as well as violent. Many are born in crowded clusters where massive stars form in groups. Surrounded by siblings, they share their radiation and winds, sculpting each other's environments. Some live with a close companion star. When two massive winds collide head-on, they carve a shock front in space, a thin curved sheet where gas is heated to extremes and particles are accelerated. That shock can shine in X-rays and radio waves and can wrap itself into spirals as the two stars orbit each other, like a slow dance traced in glowing sand. In some pairs, the companion's gravity pulls on the hypergiant's swollen atmosphere, raises tides taller than planets, and steals material that the hypergiant can barely afford to lose. In others, the companion is a collapsed remnant, a hidden neutron star, or a black hole that skims the outer layers and feeds, lighting up the region with bursts of high-energy radiation. Rotation, too, writes its signature on a hypergiant. A fast-spinning star bulges at the equator and flattens at the poles. The poles are hotter and brighter, the equator cooler and dimmer, a difference that can steer the wind into preferred directions. Over time, magnetic fields rise and tangle in the streaming gas. They catch pieces of the outflow and drag them into arcs and loops, shining traces of order in the otherwise chaotic flow. These magnetic threads can also act like a brake, bleeding away angular momentum and changing how the star evolves. In a hypergiant, nothing is small. Every force is magnified. Every small imbalance becomes a pattern written large across space. The end of a hypergiant's life is not a quiet curtain fall. The core keeps climbing the ladder of elements. Carbon fuses to neon and magnesium. Neon moves to oxygen. Oxygen to silicon. Silicon to iron. Each step proceeds faster than the last. What took millions of years at the start can take days or hours at the end. When the core becomes iron, the furnace runs out of tricks. Fusing iron does not release energy. The support fails. In a breath, the core collapses. The outer layers plummet inward. A shock forms and races outward, and the star explodes. In some cases, the explosion is normal only by the standards of this extreme family. A bright supernova that for a few weeks rivals an entire galaxy in light. In other cases, the final act is stranger. If the star is still very massive when it dies, the light pressure in its core may have been so intense that it turned photons into pairs of particles even before the end, softening the pressure that holds the core up. Without that pressure, the core contracts, heats, and bursts in a runaway that can blow the star to pieces without leaving any remnant behind. This is called a pair production runaway, but names are less important than the picture. The star burns so hot that light itself ceases to support it. The core gives way. The entire star becomes ash and light. No neutron star forms. No black hole remains. Only a cloud of heavy elements flies outward to drift and mix with the galaxy. In other cases, the core collapse is so complete that the newly formed remnant swallows the inflowing matter and grows into a black hole. If the star is spinning fast, and if the core lines up just so, narrow jets may form and punch through the layers, like drill bits of fire. When those jets reach open space, they release a flash of high-energy light that can be seen across billions of light years. To us, they last seconds or minutes. For the star, they are the entire biography condensed into a single scream. Not every hypergiant ends this way, but when it happens, it is one of the loudest messages the universe sends. For astronomers, hypergiants are both a gift and a challenge. Their light is abundant, but it is tangled with dust and sculpted by winds. To understand them, one must listen in many languages of light. The shortest waves tell of the hottest gas near the shock fronts and the deepest layers. The visible waves carry the broad lines of fast winds and the subtle fingerprints of elements in motion. The infrared glows from warm dust and shows the shapes of the shells that drift away. The radio waves reveal the slow, cold breath far from the star, where the wind has thinned and the dust cools toward darkness. Taken together, these clues allow a story to be told, not in a single snapshot, but in a time series across years and decades, because hypergiants do not sit still. They pulse and dim, brighten and erupt, and their surroundings reply. The place where a hypergiant lives matters. In small satellite galaxies near the Milky Way, the mix of heavy elements can be lower than here at home. That changes how the wind behaves. With fewer metal atoms to catch the light, the wind can be weaker, and the star holds onto its mass longer. The core grows heavier. The end can therefore be different, and the explosion brighter or dimmer, depending on the exact path taken. By comparing hypergiants in different galaxies, scientists learn how the very first massive stars might have lived in the young universe, where the chemistry was poorer and the winds perhaps gentler, allowing stars to reach sizes that are rare today. Hypergiants help set the rhythm of star formation around them. Their light ionizes nearby gas, carving cavities and lighting up clouds in soft pink and red. Their winds sweep gas into walls and knots. In the densest places, those walls can collapse under their own gravity and give birth to new stars. In other places, the winds strip away the raw material, delaying the next generation. The same star can trigger births on one side and prevent them on the other, not by choice, but by geometry. Over a few million years, the region changes from a uniform cloud into a lacework of bright filaments and dark pillars, a tapestry woven by light and wind. In some ways, what makes hypergiants strange is not any single property, but their refusal to be modest. Everything they do is oversized. They test every limit. They ask the same question over and over: how bright can a star be and still hold itself together? The answer is written in their tantrums and their scars, in the arcs of dust they have thrown off and the bubbles they have carved. It is written in the newborn stars that rise at their borders, and in the heavy elements that their deaths will return to space. Watch them long enough, and you begin to see the rhythm. There is a breath, a swelling, a pause, a letting go. Then another breath, and another letting go. When the last breath ends, the story widens to include everything the star has touched. To stand beneath a sky that contains a hypergiant is to share a galaxy with an actor that cannot be ignored. Even if you cannot see it with your eyes, its work reaches you. The calcium in your bones, the iron in your blood, the oxygen in every breath, all were cooked in the hearts of stars, and the most massive among them help stir the pot. Hypergiants do not live long enough to be common, but their rarity does not make them small. It makes them decisive. They are the cornerstones of change, the engines that push gas from quiet clouds into bright regions, the makers of dust that future planets will inherit. When we point our instruments at these stars, we are not simply collecting data. We are listening to the universe talk about power, fragility, and time. A hypergiant is powerful beyond analogy, yet its life is fragile, lived at the edge of balance, always a little too bright for its own safety. And its time is short. Perhaps that is why they fascinate us. They are reminders that splendor can be brief, and that what matters in the end is what is given back. In their deaths, they repay their debt with interest, leaving behind the ingredients for seas, rocks, clouds, and living things that will never know the name of the star that helped them be. Our journey through the strangest stars now turns again, from the unsteady fire of these giants to the cold brilliance of compact remnants that are small, dense, and packed with surprises. But before we leave, take one last look at the wide shells and the sculpted clouds, at the soft glow of dust warmed by light that has traveled only a few weeks from a surface the size of orbits. Somewhere in those shells, a future world's atoms are drifting, waiting for gravity to pull them together. Somewhere in that glow is the shape of stories not yet written, the memory of a star that burned too bright and could not help but share everything it had. Exotic white dwarfs. At the quiet end of many stars' lives lie the white dwarfs, small, dense remnants that shine only with leftover heat, no longer powered by the fusion that sustained them for millions or billions of years. Most are similar, Earth-sized spheres of carbon and oxygen, quietly cooling for eons. But among these stellar embers, there is a rare and fascinating minority, the exotic white dwarfs that break the pattern. They have strange compositions, extreme magnetic fields, unusual rotations, or histories so complicated that they seem to belong to an entirely different category of object. These stars are the rule breakers of the white dwarf family, each one carrying scars and signatures of an unusual past. To understand why these outliers are so remarkable, it helps to start with the normal. A typical white dwarf is the end stage of a star with less than about 8 times the sun's mass. When such a star exhausts its core hydrogen, it swells into a red giant, fuses helium into carbon and oxygen, and eventually blows off its outer layers into a glowing planetary nebula. The leftover core, no longer able to generate energy through fusion, collapses under gravity until it is stopped by an invisible quantum pressure, electron degeneracy pressure, that has nothing to do with heat and everything to do with the strange rules of the subatomic world. This pressure can hold the star up forever, as long as its mass stays below a critical threshold, the Chandrasekhar limit, about 1.4 times the sun's mass. The result is a dense ball of matter packed so tightly that a teaspoon of it would weigh tons, radiating slowly into the night for billions of years. Most white dwarfs have clean, predictable atmospheres. The intense gravity pulls heavier elements downward, leaving only hydrogen or helium in the thin layer we can observe. But exotic white dwarfs defy these expectations. Some are almost pure helium from the surface inward, the result of stars that lost their outer layers before they could fuse helium into heavier elements. These helium white dwarfs are often born in binary systems, where a companion star strips away material early. Because they never got the chance to fully develop, they are lighter than average, sometimes less than half the Sun's mass, and can remain surprisingly warm for their size due to interactions with their companion. Other exotic white dwarfs push in the opposite direction, toward greater mass and more complex interiors. Oxygen neon white dwarfs form from progenitors just massive enough to ignite carbon fusion, but not massive enough to collapse into a neutron star. Their cores are filled with oxygen and neon, with traces of magnesium. They are rare, massive, and on the edge of stability. If such a star gains even a little mass from the winds of a nearby companion or from a merging event, it can tip over the stability limit. When that happens, one of two fates awaits. It may collapse quietly into a neutron star, or it may ignite runaway nuclear reactions in a flash of destruction, producing an unusual and powerful thermonuclear supernova. Then, there are the magnetic white dwarfs. While many white dwarfs have faint residual magnetic fields, some have fields so powerful they rival those of neutron stars, measured in hundreds of millions or even billions of times the strength of Earth's field. These fields are not just curiosities, they shape the star's entire behavior. In some magnetic white dwarfs, the field channels in falling material from a companion star into narrow columns that strike the magnetic poles, creating bright hotspots that rotate in and out of view. The light from these regions pulses with clock-like regularity, giving clues about the star's rotation and field structure. In the most extreme cases, the field is strong enough to distort the star's atmosphere, changing the way it absorbs and emits light, and leaving a spectral fingerprint unlike anything in ordinary stars. Rapidly spinning white dwarfs form another exotic class. Most white dwarfs rotate slowly, perhaps once every hours or days, because they have shed angular momentum over their long evolution. But some spin every few minutes, or even seconds. This is usually the result of dramatic past events, a merger between two white dwarfs, or a long history of accreting material from a companion star that acted like a cosmic flywheel. Rapid rotation can slightly flatten the star at its equator and influence its magnetic field. In extreme cases, these fast rotators can mimic the behavior of pulsars, though their emission comes from different processes. Some of the most exotic white dwarfs come from mergers. In a close binary system of two white dwarfs, gravitational waves slowly rob the pair of orbital energy, bringing them closer together until they merge. If their combined mass is below the Chandrasekhar limit, the result can be a single, more massive white dwarf with an unusual composition and rapid spin. Its magnetic field may be dramatically strengthened by the turbulent mixing during the merger. Such a star can look ordinary at first glance, but its spectrum and spin reveal its turbulent history. If the combined mass exceeds the limit, the merger can ignite a Type 1, a supernova, a brilliant galaxy-wide beacon that completely destroys both stars, leaving no remnant at all. Then there are the crystallized white dwarfs. As white dwarfs cool, the ions in their interiors slow down and lock into a crystalline lattice, releasing latent heat. This process is slow, but in the oldest and coolest white dwarfs, the core can be a single, vast crystal of carbon and oxygen, essentially a diamond the size of the Earth. This crystallization delays cooling, meaning that some white dwarfs stay luminous for longer than expected. Astronomers have actually observed this effect in the cooling patterns of large white dwarf populations, confirming the predictions of theory. It is a reminder that even after nuclear fusion ends, stars can undergo quiet, beautiful transformations. One of the most telling kinds of exotic white dwarf is the polluted white dwarf. In principle, the strong gravity of a white dwarf should cause heavy elements to sink out of its atmosphere in days or weeks, leaving only hydrogen or helium visible. But some white dwarfs show atmospheric traces of calcium, iron, silicon, and other heavy elements. The best explanation is that they are actively accreting debris from disrupted asteroids, comets, or even small planets. In some cases, the chemical pattern matches that of rocky planets like Earth, suggesting the white dwarf once hosted a planetary system and is now consuming the shattered remains. This planetary cannibalism not only reveals the white dwarf's recent history, but also gives astronomers a way to study the makeup of exoplanets long after their stars have died. Even stranger are the hot DQ white dwarfs, whose atmospheres are dominated by carbon. Their origins are still uncertain. They may be the remnants of massive stars that lost their hydrogen and helium layers through violent winds or mergers. They are rare, hot, and short-lived in their current form, making them difficult to study in large numbers. Other rare subtypes include ultramassive white dwarfs, close to or even above the Chandrasekhar limit, that seem stable for now, but may collapse in the future, and peculiar magnetic rotators whose light curves defy easy explanation. The study of exotic white dwarfs is not just about cataloging curiosities. These stars test our understanding of physics under extreme conditions. In their dense interiors, matter is compressed to densities millions of times greater than anything on Earth, and electrons move in ways that only quantum mechanics can describe. In magnetic white dwarfs, the field strength can alter atomic structures themselves, changing how atoms absorb light. In polluted white dwarfs, we can see direct evidence of the ongoing destruction of planetary systems. In crystallized white dwarfs, we witness the slow solidification of a star's heart. Each of these processes pushes the limits of what we know about matter, magnetism, and stellar evolution. Astronomers study exotic white dwarfs with a variety of tools. Spectroscopy can reveal the atmospheric composition, magnetic field strength, and temperature. Photometry, measuring the brightness over time, can detect pulsations or rotation periods. In some cases, pulsating white dwarfs allow for asteroseismology, the study of stellar quakes that can map the internal structure. Binary companions provide opportunities to measure mass and radius precisely, while X-ray and ultraviolet observations can reveal hotspots where infalling material strikes the surface. Even gravitational wave observatories may someday detect the mergers that create some of these unusual stars. White dwarfs are also essential to the cosmic ecosystem. While they no longer fuse elements, they contribute in other ways. In binary systems, they can trigger novae, sudden bright outbursts when accreted hydrogen ignites on the surface. In mergers or, when pushed over the Chandrasekhar limit, they can produce supernovae that seed the galaxy with heavy elements. Polluted white dwarfs are recycling planetary material into interstellar space, where it may one day form new stars and planets. Even in their quiet cooling phases, they are part of the slow turnover of matter in the galaxy. Perhaps the most striking thing about exotic white dwarfs is their variety. Each one is a record of a unique life story. A helium white dwarf stripped by a companion before it matured. A magnetic giant spun up by a merger. A diamond cored remnant shining with the glow of ancient heat. A cannibal star feasting on the remains of its planets. They are the final chapters of stellar biographies that took unusual turns. And their diversity reminds us that the path from birth to death for a star is not always straightforward. In the grand catalog of strange stars, exotic white dwarfs might seem less dramatic than hypergiants or neutron stars. They do not explode in titanic bursts of light or warp space as black holes do. Yet in their quiet way, they are every bit as compelling. They hold secrets about stellar evolution, planetary systems, and the physics of matter itself. And while they will slowly fade into blackness over trillions of years, they will do so carrying the marks of the unusual events that shaped them, silent witnesses to the strange turns a star's life can take. Brown dwarfs and dark stars. Between the smallest true stars and the largest planets lies a shadowy category of objects that defies easy classification. These are the brown dwarfs, sometimes called failed stars. Though that label hardly captures their complexity or their quiet importance in the galaxy. Too small to sustain the continuous hydrogen fusion that powers stars like our Sun, yet far larger and hotter than even the most massive planets, brown dwarfs occupy a unique space in the cosmic spectrum. They are the in-betweeners, bridging the gap between star and planet, and their study has revealed much about how objects form, evolve, and shine, or fail to shine, in the vastness of space. Brown dwarfs are defined primarily by mass. To ignite hydrogen fusion in their cores, an object needs to be at least about 75 to 80 times the mass of Jupiter. brown dwarfs fall below this threshold, ranging from roughly 13 to 75 Jupiter masses. 13 is a significant number because at that mass, an object can briefly fuse deuterium, a heavier isotope of hydrogen. Deuterium fusion requires less heat and pressure than ordinary hydrogen fusion. So many brown dwarfs pass through a short phase of deuterium burning early in their lives before cooling and fading. In the most massive brown dwarfs, there may also be a brief period of lithium fusion, but this too is fleeting. Once these fuels are exhausted, no new nuclear reactions occur, and the brown dwarf cools steadily over time. Because they lack ongoing fusion, brown dwarfs do not have the steady energy output of true stars. Instead, they shine faintly in infrared light, glowing with the residual heat left over from their formation. Young brown dwarfs can be surprisingly bright in infrared, their surfaces glowing at thousands of degrees Kelvin, but as they age they fade and cool, eventually becoming almost undetectable in visible light. The oldest and smallest may be barely warmer than the outer planets in our solar system, their light hidden deep in the infrared spectrum. This makes them notoriously difficult to find. And it is only in the last few decades, with sensitive infrared surveys, that we have begun to detect them in large numbers. Brown dwarfs come in a variety of spectral types, labeled L, T, and Y, which describe their temperatures and the chemistry of their atmospheres. L-type brown dwarfs are the hottest and youngest, with temperatures between about 1,300 and 2,500 degrees Celsius. Their atmospheres often contain clouds of iron and silicate dust, making them appear reddish in infrared images. T-type brown dwarfs are cooler, between about 500 and 1,300 degrees Celsius, and their atmospheres are dominated by methane absorption, much like the giant planets Jupiter and Saturn. The coolest known are the Y-type brown dwarfs, with temperatures as low as room temperature here on Earth. These frigid bodies barely glow at all, and their discovery has stretched the limits of our infrared telescopes. One of the most interesting things about brown dwarfs is that they form like stars, but evolve more like planets. They are born in collapsing clouds of gas and dust, just as stars are. Gravity pulls material together into a dense core, and the object heats up as it contracts. For a true star, this process ends when the core becomes hot and dense enough for hydrogen fusion to begin, halting further collapse. For a brown dwarf, that ignition point is never reached, and so it begins its life already cooling. In a sense, brown dwarfs are stars whose engines never quite started. Despite their nickname, failed stars, brown dwarfs are not failures in any real sense. They are a natural outcome of the star formation process, and they may be nearly as common as true stars. Some estimates suggest that for every star like our Sun, there may be a similar number of brown dwarfs, quietly drifting in the galaxy's dark spaces. Many are solitary, but others orbit stars, sometimes at great distances. And still others exist in binary systems with other brown dwarfs, or low-mass stars. The line between brown dwarf and planet is not as clear as the mass-based definition might suggest. A giant planet like Jupiter forms in a circumstellar disk around a young star, accreting material over time. A brown dwarf forms directly from the collapse of a cloud fragment, independent of a disk. Yet, in terms of size, the largest planets and smallest brown dwarfs can be almost identical. This has led to debates over whether some objects are truly planets or simply low-mass brown dwarfs. The history of their formation matters just as much as their mass and temperature. Some brown dwarfs have been found with weather systems, much like planets. Observations have revealed rotating cloud patterns, storms, and even signs of atmospheric variability over time. In the cooler T and Y types, these clouds may be made of exotic substances like ammonia ice, while in hotter L types, they may contain droplets of molten iron or silicates. Watching these patterns change has given astronomers a rare chance to study weather on worlds beyond our solar system, in environments far more extreme than anything on Earth. Another fascinating aspect of brown dwarfs is their role as companions. In some binary systems, a brown dwarf orbits a main sequence star, its faint glow lost in the glare of its brighter partner. Detecting these companions requires careful measurement of the star's motion or direct imaging in the infrared. In other systems, brown dwarfs orbit each other, forming binaries that offer rare opportunities to measure mass directly. These measurements are crucial for testing theoretical models of how brown dwarfs evolve over time. While brown dwarfs never ignite sustained hydrogen fusion, they still change dramatically over their lifetimes. A young brown dwarf may start out hot and bright in the infrared, but over billions of years, it cools and fades. Eventually, it becomes a cold, dark object, still massive, still dense, but radiating almost no heat. At that point, it would be all but invisible to our current telescopes. This has led to speculation about the existence of dark stars in the galaxy. Ancient brown dwarfs, so old and cool that they no longer emit detectable radiation. They would be among the most elusive objects in the universe, detectable only by their gravitational influence on nearby stars, or through the faintest possible infrared signatures. The idea of dark stars pushes into the realm of the hypothetical, but it is a logical extension of the life cycle of a brown dwarf. Given enough time, trillions of years, every brown dwarf will eventually fade into such a state. Our universe is not yet old enough for any to have reached complete darkness, but the oldest brown dwarfs we have found are already so cool that they are barely distinguishable from giant planets. In the unimaginably far future, when all normal stars have burned out, the universe may be filled with such dark remnants, along with cold white dwarfs, neutron stars, and black holes, a cosmic graveyard lit only by the occasional collision or decay. Studying brown dwarfs and their eventual fate has broader implications. They challenge our understanding of where the boundaries between stars and planets truly lie. They help refine our models of star formation, showing that the process does not have a sharp cutoff at the hydrogen burning limit. They offer laboratories for studying atmospheric physics under exotic conditions, with temperatures, pressures, and chemical compositions unlike anything on Earth. And because they are so common and long-lived, they may hold clues to the overall structure and evolution of our galaxy. Detection techniques for brown dwarfs have advanced rapidly in recent years. Infrared surveys such as those conducted by the Wide Field Infrared Survey Explorer, WISE, have uncovered hundreds of these objects, some within just a few light years of the Sun. The nearest known brown dwarf system, Lumen 16, lies only about 6 light-years away and consists of 2 brown dwarfs orbiting each other. Such nearby examples allow for detailed study, including measurements of weather patterns, rotation rates, and atmospheric composition. Even with these discoveries, brown dwarfs remain mysterious. Their exact numbers are uncertain, and their lower mass limit, below which no deuterium fusion can occur, is still debated. Some objects thought to be planets may turn out to be brown dwarfs, and vice versa. The coming decades, with more powerful infrared telescopes and perhaps direct imaging of cooler and smaller brown dwarfs, will likely bring many surprises. In the story of strange stars, brown dwarfs occupy a subtle but essential chapter. They are not the explosive giants or the dense corpses of massive stars, but they represent a quiet, enduring population, scattered through the galaxy in numbers that may rival the stars themselves. They remind us that the universe is not composed only of the bright and the violent. It is also shaped by the faint and the overlooked, the objects that do their work in the shadows. And while they may lack the glamour of a supernova or the crushing gravity of a black hole, brown dwarfs have their own quiet power. They are the cosmic in-betweens, too massive to be planets, too small to be stars, forever holding their place in the narrow band between light and darkness. As they cool over the ages, some may one day cross entirely into the realm of the dark stars, invisible to our eyes but still shaping the galaxy through their gravity. In that far future, when the universe has grown old and dim, these once warm embers will drift endlessly, reminders of a time when the cosmos was young and still full of light. Preon stars and other hypotheticals. In the vast menagerie of stellar objects we have discovered, there are some whose existence we can observe directly: bright giants, dense neutron stars, cooling white dwarfs. But there is another realm, one that exists mostly on the chalkboards of theoretical physicists and in the outputs of high-powered computer simulations. This is the realm of hypothetical stars, objects that may never have formed in our universe, or that might exist only under conditions so extreme we have yet to find them. Among these exotic possibilities, one of the most intriguing is the Preon star, a proposed object even denser and stranger than a neutron star or Quark star. To understand Preon stars, we have to go deep into the hierarchy of matter. Most people know that atoms are made of protons, neutrons, and electrons. Inside the protons and neutrons are smaller particles called quarks, bound together by the strong nuclear force. The standard model of particle physics treats quarks as fundamental, meaning they are not made of anything smaller. But some theoretical models suggest that quarks themselves may be composed of still smaller entities, which have been nicknamed preons. If preons are real, they could open the door to an entirely new form of matter. In a neutron star, matter is packed so tightly that individual atoms no longer exist. Electrons and protons merge into neutrons, and the star becomes a giant ball of nuclear matter. In a hypothetical quark star, the pressure is so intense that even neutrons dissolve into their constituent quarks, producing a dense soup called quark matter. But if we go one step further, if the pressure becomes high enough to break quarks apart into preons, we would get preon matter. A preon star would be a massive ball of this ultra-dense material, with densities trillions of times greater than water, far beyond even quark matter. The density of a preon star is almost beyond comprehension. A neutron star packs the mass of the Sun into a sphere about 20 kilometers across. A preon star, if it existed with similar mass, could be as small as a mountain or even a large asteroid. This extreme density would create gravitational fields approaching those of black holes, but without forming an event horizon. In fact, one of the puzzles with preon stars is whether they could exist without immediately collapsing into a black hole. The balance between gravity and whatever quantum pressure might resist it is still a matter of speculation. No preon stars have been observed, and their existence remains entirely theoretical. Detecting one would be extremely difficult because their small size and lack of luminous emission would make them almost invisible unless they passed close to us or interacted with other objects. Some have speculated that certain unexplained gravitational lensing events, where the light from a distant star is bent by an unseen mass, could be caused by preon stars or other exotic compact objects. But the data so far is inconclusive. Preon stars are not the only hypothetical stars that have captured the imagination of astronomers and physicists. Another example is the boson star, which would be made not of ordinary matter, but of bosons, particles that follow very different rules from the fermions that make up atoms. Bosons can occupy the same quantum state, meaning they can pile up in ways that fermions cannot. This could allow a boson star to exist without the same kind of degeneracy pressure that supports neutron stars and white dwarfs. If the boson in question were the Higgs boson or some other yet undiscovered particle, a boson star could have entirely new properties, perhaps even mimicking the gravitational pull of a black hole without an event horizon. There are also hypothetical dark matter stars. Dark matter is an invisible form of matter that interacts gravitationally, but not, as far as we know, with light. In the early universe, before normal stars formed, it's possible that clumps of dark matter could have collapsed under their own gravity. If dark matter particles can annihilate with each other, such a collapse could have released enormous amounts of energy, forming a dark star that shone not with nuclear fusion, but with dark matter annihilation. These objects might have been huge, larger than entire planetary systems, and could have played a role in the formation of galaxies. None have been seen, but upcoming telescopes may be able to detect the faint infrared signatures of such objects from the early universe. Still other hypothetical stars emerge from the idea of quasi-stars. These would have formed in the very early universe when massive clouds of gas collapsed directly into black holes of thousands of solar masses. Before the collapse completed, the energy from the infalling material could have created a bloated envelope of hot gas around the forming black hole, shining like a star, but powered entirely by accretion. Quasi-stars could have been some of the brightest objects in the young universe, but they would have been short-lived, lasting only a few million years before the envelope dissipated and the black hole was left behind. In the family of exotic possibilities, there are also electroweak stars. These are hypothetical objects in which the pressures and temperatures in the core are high enough to trigger electroweak interactions, the process by which quarks can be converted into leptons via the unified electroweak force. This would release vast amounts of energy without the need for nuclear fusion. An electroweak star could potentially shine for millions of years in a stable state, even without fusion reactions. Such a star would have a core where matter exists in conditions that have not been seen since fractions of a second after the Big Bang. Preon stars, boson stars, dark stars, quasi-stars, and electroweak stars all share one thing. They stretch the limits of our understanding of physics. Each one requires conditions far beyond what we have been able to test in laboratories, relying instead on the extrapolation of known physics into realms of extreme density, temperature, and energy. Some of these ideas may never be more than mathematical curiosities. Others may one day be confirmed by indirect evidence through gravitational lensing, unusual gravitational wave signatures, or unexplained emissions. Studying hypothetical stars is not an idle exercise. Even if these objects do not exist in our universe, the theories behind them help physicists explore the boundaries of known physics. By thinking about what might happen at densities far beyond those of neutron stars, researchers can test how well our models hold up. If those models break down, it may point the way toward new physics, new particles, new forces, or new relationships between the ones we already know. There's also the possibility that some of these objects could explain existing mysteries. For example, if Preon stars or boson stars exist, they might account for some of the dark matter in the universe. If quasi-stars formed in the early universe, they might have seeded the supermassive black holes we see at the centers of galaxies today. Electroweak stars, if real, could provide a rare, steady-state laboratory for conditions otherwise only available for an instant in particle accelerators. Hypothetical stars also serve as a reminder that the universe is not limited to what we have already observed. Just as neutron stars were once only a theoretical prediction, and exoplanets were speculative until the 1990s, some of these exotic ideas might move from theory to reality as technology advances. Instruments sensitive to gravitational waves, high-energy neutrinos, or faint infrared glows may one day catch hints of these elusive objects. In the grand catalog of strange stars, hypothetical stars like Preon stars are perhaps the strangest of all. They may exist only on paper, but they represent the ultimate challenge, to imagine the universe not only as it is, but as it could be under the most extreme and exotic conditions. They remind us that the boundaries of possibility are often set not by the universe itself, but by the limits of our imagination, and that beyond every confirmed discovery lies an ocean of what-ifs waiting to be explored. I hope you enjoyed this journey through the most unusual stars in the universe. If you're still awake, you can find another exciting journey right here on the screen that I think you'll really enjoy. Until the next video, and have a good night.